This week, we'll start exploring an important concept in programming: branching. Branching allows programs to make decisions and follow different paths depending on conditions. But before we dive into branching, it's important to review the foundation that makes branching possible: data types. Data types determine what kind of information our program is working with: numbers, text, or logical values, and they guide how decisions can be made. So first, we'll take a closer look at data types, and then we'll build on that knowledge to understand how branching works. Python has three fundamental types. Text type. This is called a string or str. A string is simply text enclosed in single or double quotes. Numeric types. These include two categories: integers, int, for whole numbers, such as 23 or 12. Floats, float, for decimal numbers, such as 3.14 or zero point 0.5. Boolean type. This is represented by bool, which can only take on one of two values: true or false. These basic data types are important because they define the kind of information we're working with. How do we then check what type of data a variable holds? Python gives us a built-in function called type. This function tells us the data type of any object. For example, if we write x equals 5 and then call print type x, Python will tell us that x is of type class int, which means it's an integer. This is a really useful tool when you're not sure what type of data you're working with, especially when dealing with user input or more complex programs. We'll use this often to double-check what's inside our variables. Now let's think about something very basic. How many different numbers can we represent with just a single bit? A bit is the smallest unit of information in a computer, and it can only take on one of two possible values: 0 or 1. So with one bit, we can represent exactly two numbers. This might seem simple, but it's the foundation of everything in computing. Now let's extend the idea. What if we use two bits instead of just one? Each bit can take on two possible values: 0 or 1. So with two bits, we can form combinations: 0001, 1011. That gives us four different numbers we can represent with two bits. In general, the number of possible combinations is calculated as 2 to the power of the number of bits. So with two bits, we get 2 times 2, which is 4 possible values. With 3 bits, we get 2 times 2 times 2, which is 8 possible values. A byte is made up of 8 bits. Since each bit has 2 possible values, that's the same as 2 to the power of 8, which equals 256. So far, we've talked about using bits to represent positive numbers. But what about negative numbers? The way computers handle this is by using one of the bits as a sign bit. If the sign bit is 0, the number is positive. If the sign bit is 1, the number is negative. That means in an 8-bit byte, only 7 bits are left to represent the actual value of the number. So instead of 2 to the 8th power equals 256 values, we now have 2 to the 7th power equals 128 values available for the magnitude. This is the basic idea behind signed numbers in binary. In practice, computers use a system called 2's complement, which makes arithmetic easier and avoids having two versions of 0. But the main idea is that one bit is reserved for the sign, and the remaining bits are used for the number itself. Now let's look at how integers are typically stored in most programming languages. An integer is usually represented using 4 bytes, which is the same as 32 bits. Since each bit can store two values, the total number of different integers that can be represented with 32 bits is 2 to the power of 32, which equals about 4.29 billion possible values. If the integers are unsigned, only positive numbers, that means we can count from 0 all the way up to 4,294,967,295. If the integers are signed, positive and negative, then half of those values are used for negative numbers and half are used for positive numbers. That gives us a range of about negative 2.1 billion to positive 2.1 billion. This is the standard integer size in many languages like C, C++, and Java. Here's an example in Java that shows the limitation of using 32-bit integers. In this program, we declare an integer variable and try to assign it the value 4,294,967,296. That's exactly one more than 2 to the power of 32. When we try to compile and run the code, Java throws an error saying the literal is out of range. Let's try to assign a smaller value, 2,147,483,648 to an integer. But notice what happens. The compiler still gives an error. Why? Because the maximum value for a signed 32-bit integer is 2,147,483,647. That's the highest positive number that can be represented when one bit is reserved for the sign. So when we go just one number higher, Java tells us the value is out of range. This demonstrates an important point. A 32-bit integer can hold values from negative 2,147,483,648 up to plus 2,147,483,647 if signed. Anything outside this range cannot be represented with a standard integer in Java. In Java, integers have a fixed size. If you try to go beyond that range in Java, the result is either an error or unexpected behavior. Python, however, works differently. In Python 3, integers are not restricted to 32 or even 64 bits. They can grow as large as your computer's memory allows. For example, you can assign an extremely large number to a variable, and Python will handle it without any problem. This flexibility is one reason Python is widely used in scientific computing and data analysis. It allows developers to work with very large numbers without worrying about overflow. A real-world example of this is cryptography. Modern encryption algorithms, such as RSA, depend on numbers that are hundreds or even thousands of digits long. These values are far too large for fixed-size integers. Python's arbitrary precision integers make it possible to work with encryption keys, large prime numbers, and other massive calculations seamlessly. So while languages like Java or C use fixed integer sizes for performance reasons, Python trades a little speed for flexibility, making it especially powerful for applications in cryptography, data science, and even astronomy. What would this calculation print out? At first glance, you'd probably expect this to equal 0, but when you run this code in Python, the output is not exactly 0. Why does this happen? It's because of how computers store floating point numbers. Numbers like 0.1 or 0.2 cannot be represented exactly in binary. Instead, the computer stores an approximation. When you add and subtract these approximations, tiny rounding errors appear in the result. Here is another example. Why is 0.1 plus 0.2 not exactly equal to 0.3 in Python? If you run it, Python shows 0.3 followed by 15 zeros and 4. That tiny extra piece comes from a round-off error. Similarly, if you add 0.3 plus 0.6, Python shows 0.8 and then 15 nines instead of exactly 0.9. The reason is that computers store numbers in binary, and many decimal fractions, like 0.1 or 0.2, cannot be represented exactly in binary form. Instead, the computer stores the closest approximation. When we do arithmetic on those approximations, the small errors become visible in the result. This isn't unique to Python. It happens in virtually every programming language that uses floating point numbers. Floating point arithmetic is approximate. For most applications, the errors are tiny and don't matter. But if you need exact precision, such as in finance, you should use special tools like Python's decimal module. Now let's talk about conditions. A condition is simply a Boolean expression, something that evaluates to either true or false. For example, if we check whether 7 is greater than 8, Python evaluates this as false because 7 is not greater than 8. On the other hand, if we check whether 8 is greater than 7, Python evaluates this as true since 8 is indeed greater than 7. Conditions are essential in programming because they let us control the flow of our programs. Later, when we use branching statements like if, elif, and else, these conditions will determine which path the program takes. When we write conditions in Python, we use comparison operators. Most of them are pretty straightforward, like greater than or less than. The ones that trip people up are the equal and not equal operators. In Python, to check if two things are equal, we don't use a single equal sign. That's for assignment. Instead, we use two equal signs. So if I write x, two equal signs y, I'm asking Python, are these two values the same? On the other hand, if I want to check that two things are different, I use exclamation mark equals. So X exclamation mark equals Y is Python's way of saying, are these two values not equal? These two are especially important to get right because you'll use them constantly in branching statements when your program needs to make decisions. For example, in this code, we set grade equals 100. That part is fine. But then in the if statement, the condition is written as if grade single equal sign 0. This causes a syntax error because Python is expecting a Boolean expression, but instead sees an assignment. What we really meant was if grade 2 equals sign 0 to check whether the grade equals 0. So remember, single equal signs means store this value. Two equal signs means check if two things are the same. Mixing these up is a very common source of errors, even for experienced programmers. Now we will look at one of the most important ideas in programming, branching. Up to now, our programs have just run line by line from top to bottom. But real programs need to make choices. Branching lets us do exactly that. With branching, a program can ask a question, check a condition, and then take one path if the answer is true, or another path if it's false. It's how we teach our programs to make decisions, just like we do in everyday life. When we talk about branching in programming, we're really talking about decision-making. Think about buying a car. If you go to Tesla's website, you don't just see one option. You're given choices: Model S, Model 3, Model X, Model Y. Depending on what you click, the website shows you different information and guides you down a different path. That's exactly what branching does in a program. The program asks a question, like, which model do you want? And then takes the appropriate path based on your decision. So branching is how we build programs that don't just run straight through, but instead respond to input and make choices just like we do. A flowchart is a diagram that shows the steps in a process or workflow. You can think of it as a visual way to represent an algorithm, a step-by-step approach to solving a problem. The shapes in a flowchart usually mean different things. Rectangles represent actions, diamonds represent decisions, and arrows show the direction of the flow. Take the example on this slide. It shows how you might troubleshoot a lamp that doesn't work. First, the flowchart asks, is the lamp plugged in? If not, the solution is to plug it in. If it is, the next question is the bulb burned out? If yes, replace the bulb. If not, then you repair the lamp. This is exactly how computers make decisions, step by step, following conditions and branching paths. Flowcharts give us a way to plan that logic visually before we write the actual code. When we draw flowcharts, we use different shapes to represent different kinds of steps. These shapes are part of a standard, so once you learn them, you'll be able to read almost any flowchart. The arrow shows the flow of control. What step comes next? The oval, called a terminal, marks the beginning or the end of a process. You'll often see it labeled with words like start or end. The rectangle represents a process, meaning an action or operation. For example, this could be a step like calculate total or print result. Finally, the diamond is used for decisions. This is where the program asks a yes-no question or a true-false test. Depending on the answer, the flow goes down one path or the other. By combining these symbols, we can describe almost any algorithm in a clear, visual way before writing it as code. When we talk about decision-making in programming, we're talking about those moments where the program has to choose between different paths. Take the Tesla website as an example. You're given options: Model S, Model 3, Model X, Model Y, and depending on which one you click, the website takes you down a different path and shows you specific information. Now the question is, how do we represent this kind of logic visually? That's where a flowchart comes in. In a flowchart, decisions are shown using a diamond shape. Each decision asks a yes, no question or checks a condition, and then the flow continues in one direction or another. So the challenge here is, how would we use a flowchart to represent the logic behind this website, where a single choice leads to different outcomes? As humans, we're really good at making choices from a list of options. If you go to a website and see 4 different Tesla models, you can instantly pick the one you want without any confusion. But computers typically don't work that way. They're actually much dumber than we often think. A program can't just look at four options and say, okay, I'll take that one. Instead, it needs to go step by step, asking a chain of yes or no questions. This flowchart shows how a computer actually handles the decision-making process. Notice that instead of picking directly from all four Tesla models, the program has to go step by step. First, it asks, did the user choose Model S? If yes, we're done. If not, it moves on to the next question. Did the user choose Model 3? If the answer is no again, it keeps going. Did the user choose Model X? And finally, did the user choose Model Y? Each step is just a simple yes or no question. That's because computers can't evaluate multiple options in one go the way humans can. They break the problem down into a sequence of smaller decisions. This is exactly what branching looks like in programming, a chain of conditions that narrows down the choices until the program finds the right outcome. This is the basic structure of an if statement in Python. It starts with the keyword if, followed by a condition, and then a colon. The condition is a Boolean expression. It evaluates to either true or false. If the condition is true, the code inside the block will run. If the condition is false, Python skips over it. The important part to notice here is indentation. In Python, indentation is not optional. It's how Python knows which statements belong inside the if block. Every line that should run only when the condition is true must be indented the same amount. So the pattern is simple. If condition, do something. This is the building block of all decision-making in Python. Here's a simple example of an if statement in action. We set grade equals 85. Then we check the condition. If grade greater than or equal to 60. Since 85 is greater than or equal to 60, the condition is true, so Python runs the indented code inside the block. Print passed. The result is that the word passed is printed on the screen. If the condition had been false, nothing would happen. In this case, since the grade is high enough, the program executes the statement. Below you can see the same logic represented as a flowchart. The diamond shows the decision. Is the grade greater than or equal to 60? If the answer is true, the program prints passed. If the answer is false, the program simply skips over the print statement and ends. This shows how the flowchart and the code are connected. The same decision-making logic is just written in two different forms. An if-else statement lets us handle two possibilities instead of just one. It starts with if condition. If the condition is true, Python runs the indented code inside that block. But if the condition is false, Python skips the first block and runs the code under else instead. So the logic works like this. Check the condition. If it's true, do one thing. If it's false, do the other. This guarantees that the program always makes a choice. It will run exactly one of the two blocks depending on the result of the condition. Here's an example of how an if-else statement works in practice. We set grade equals 85. Then the program checks the condition. If grade greater than or equal to 60. Since 85 is greater than 60, the condition is true. So Python runs the first block of code and prints passed. But if the grade had been less than 60, the condition would be false, and Python would skip the first block and go straight to the else block. Printing failed. The flowchart below shows the same logic visually. The decision diamond asks, is grade greater than or equal to 60? If yes, follow the true branch and print passed. If no, follow the false branch and print failed. This structure ensures that no matter what the grade is, the program always produces an output, either passed or failed. So far, we've seen how if lets us check one condition, and if else lets us handle two possibilities. But what if we have more than two options? That's where ELIF comes in. ELIF stands for else if. It allows us to check multiple conditions, one after the other. Here's how it works. First, Python checks the if condition. If it's true, that block runs and the rest are skipped. If it's false, Python moves on to the elif condition. If that's true, it runs that block and skips the rest. Finally, if none of the conditions are true, the else block runs as a fallback. This gives us a way to create a chain of decisions instead of being limited to just two outcomes. Here's a practical example of an if-else statement. We've set grade equals 85. The program first checks the condition if grade greater than or equal to 90. Since 85 is not greater than or equal to 90, that condition is false, so Python skips it. Next, it checks the first elif, grade greater than or equal to 80. This time the condition is true, so the program runs the statement inside that block and prints B. After that, the program doesn't check any of the other conditions. Once one condition is true, Python runs that block and ignores the rest. If none of the conditions had been true, the program would have fallen through to the else block and printed F. This structure lets us handle multiple possibilities in a clean, step-by-step way, instead of writing a long chain of separate if statements. This flowchart shows how an if, else statement works behind the scenes. The program starts at the top and checks the first condition. If that condition is true, it runs the code inside the if block and then exits the chain. If the first condition is false, the program moves on to the next test, the elif. If that condition is true, it runs the corresponding block. If it's false, it continues checking the next elif, and so on. Eventually, if none of the conditions are true, the program reaches the else block at the bottom and runs that as the default case. The key idea is that the program follows this chain step by step, but only one block ever runs, the first one with a true condition. Once a match is found, the rest are ignored. One important thing to know is that the else part of an if, else statement is optional. That means you don't always have to include it. If you only care about certain conditions being true, you can just use if or if and skip the else. In that case, if none of the conditions are true, the program simply does nothing and moves on. So else is useful when you want to make sure there's always a fallback action, but if you don't need that default case, you can leave it out. Python also has something called a conditional expression, sometimes called a one-liner if else. This reads almost like plain English. Result is passed if grade is greater than or equal to 60, otherwise failed. Python programmers do use this, especially when they want to write something short and simple. But for now, don't use this style yet. We're still practicing with the full if, else statements so you can clearly see the logic step by step. Later on, once you're comfortable, we'll come back to this shorthand way of writing conditions. Thank you. This presentation was prepared by June Lee with the assistance of AI technology.